Okay, so 7.4 characteristics of logarithmic functions with base 10 and base e. So look at the investigate the math here in our textbook. It says this: Randy came across a new type of function in his chemistry class. He learned that the pH of a solution is determined by a logarithmic function. He wondered how the characteristics of these functions differ from the characteristics of polynomial and exponential functions. Randy noticed that he had a big log button on his calculator. So you'll notice that you have a log button on your calculator if you have a scientific calculator. So he looked in his user manual and discovered that it was a base 10 logarithm. This is page 274. Using this button, he created a table of values for each of the functions below to investigate the similarities and differences. So we're going to focus on just this right here, the basic log 10 graph. Okay? Now, if you try this out on your calculator, which I would invite you to do that. So we're going to focus today on the log of x base 10. And if you look on your calculator, you have a log button, and it doesn't show any little base there, little subscript. That's called the base, okay? And it doesn't show any little subscript number there. And that's because the common logarithm is base 10. And so the log button on your calculator is log base 10. All right, so what does that mean? Well, before we get into understanding what log actually is or means or refers to, let's take a look at this chart that Randy made here. So if you type in log of -1, your calculator will say that's a non-real answer. So you can't do log of -1. Oh, interesting. What about log of 0? Well, he's done some work for us here, Randy has. And log of 0 is also undefined. Okay. So what about log of 1? Log of 1, and we're confirming this graph here. It's 0. Okay. We're not going to go through all of them, but you can see that if you type in log of 2, you're going to get a number, but it's a decimal. And as those numbers, those x values work up to 10, notice how 0.3, 0.4, 0.6, 0.6, 0.7, 0.8, 0.9, and then log of 10 is 1. Log of 10, base 10, is 1. That's very, very interesting. Okay, so a couple things we notice on all three of these graphs is that log of 1, and it doesn't matter what the base is or what this number is in front, log of 1 is 0 on all three. Okay, and so let's go back to our notes here, and in our notes I have this table of values here. Now, I also put on here a recall the exponential function. So exponential functions, we know how they work, right? If you put in a number, I'll change the color for you there. If you put in a number for x and plug it in here, so 10 to the power of 0 is, what's 10 to the power of 0? That's 1, right? What's 10 to the power of 1? Well, that's 10. 10 to the power of 2 is 100. Okay? And we can do negatives as well. So we know from our first chapter, this is what I've graphed here. This is an exponential. Okay? Now, you should notice a couple things. I want to highlight just a couple things here. Exponential, x is 0, y is 1. Logarithm, x is 1, y is 0. Another thing here, x is 1, y is 10 on the exponential, x is 10, y is 1. So that's pretty interesting to note. So logarithms are a little bit different. Now, I want you to notice a couple things here. I guess the first thing I want you to notice is that on your log button, and if you can, I don't know if you can even see that, but you should have the inverse function there is 10 to the power of x. You see that? Okay. So the exponential function of 10 to the power of x is actually the inverse of the log. And in in math, now in chapter 5, converse was reverse, right? But when we're talking about functions, inverse on your calculator, inverse means reverse. Reverse x and y. So these functions are related, okay? The exponential and the logarithm are inverse functions, and we'll talk a little bit more about that in a few minutes. Now, I'm going to insert here the base of base 10, okay? And I'm going to do some more numbers here. So x, y, and you should do this too. So we know that when x is 1, log of x, or log of 1, is 0. We also know that when x is 10, the log of 10, base 10, is 1. What is the log of 100? Yeah. The log of 100, it's correct. The log of 100 you said was 2. So let me just try and get that in here. Log of 100 is 2. Oh, that's interesting. What's the log of 1,000? Yeah, if you do that on your calculator, the log of 1,000 is 3. The log of 10,000, so the last one I'll do, is 4. Okay, so you should be noticing some patterns here. You know, something to do with the number of zeros, perhaps, on these numbers. Hey, that's interesting. Okay. But more importantly, what I want you to notice is that these numbers on the right, so the y here, that's these numbers right here, would be exponents for something. Exponents. Look at the base here. The base of the logarithm is 10. So watch this. If we did 10 to the power of 0, we get 1. 10 to the power of 1 is 10. 10 squared is 100. 10 cubed is 1,000, and so on. 10 to the 4th is 10,000. So what does that mean? Well, it means this. Here's the form for a log function. That's just right out of your textbook. Y equals a log b, or log of x base b. So this base is a base, and it's similar to the base in the exponential. Okay? So think about this number right here, this 10 over here, as the same as the base over here in the exponential. So this is the base, and this is the base. Okay? Now the difference is that this x is the exponent over here, and if we're thinking about exponents, this y is the exponent. So that means in log functions, the log provides for us an exponent. So logarithm functions are looking for exponents, or they're yielding exponents. So the log really is equal to exponent. You want to think exponent there for the base of the logarithm. All right, so I'm actually going to, just going to focus on this log right here, okay? Now, log of x base 2. So obviously we have a different base here. We had 10 before, we have base 2 now. You can't do this on your calculator. Most calculators, you don't have a choice to alter the base. Some calculators do, but most don't. Well, most only use the common base 10. But if I take the log of 4 base 2, what I'm actually asking for over here is the exponent for the base. So what exponent do I put this base to get this number? Or 2 to the power of what equals 4? Yeah, I'm looking for a 2 there. So log of 4 base 2 is 2. I'm going to have to do a bunch of examples here, I think, before you get it. That's okay, though. So what's the log of 8 base 2? Well, I'm looking for an exponent that what I raise 2 to the power of what exponent gives me 8, you see? So base, exponent, value. So 2 to the power of what gives me 8? 3. So 3 goes in there. Okay, so let's go back to base 10. That's our friend, base 10. Okay, so I can show this as base 10 like that. Okay, and I'm going to put a 10 over here. Can you guys see that all right? The red-ish? So. You guys like the yellow better, don't you? Okay, I'll do the yellow. So I like to think of logs in terms of exponential functions. That's how it's easiest for me. So this is what I do. I literally do this. 10 to the power of this equals this. So 10 to the power of what gives me what? Now, obviously 8 is going to be a little tricky, but let's just go back to our textbook. Look at this log, okay? So 10 to the power, or log of 8 base 10, log of 8 base 10 is 0.903. Oh, interesting. So 10 to the power of what gives me 8? Well, 10 to the power of 0 is 1. 10 to the power of 1 is 10. So it's got to be between 0 and 1. And as it turns out, log of 8 base 10, 0.903. What that means is 0.903 is the exponent here come on. It's the exponent that would go on 10 to produce 8. So 10 to the power of 0.903 is going to be pretty close to 8 there, 7.99 maybe, because we rounded. Okay, so if we put different numbers in here, you can probably shout out to me some answers. Let's just try this, okay? So if I put in 100 here, what's this? 2. Yeah, 2 is correct. 2. So the log of 100 is 2. What's the log of 1,000? 3. What's the log of 10,000? 4, okay? Because 10 to the power of 4 is 10,000. All right. Now, hopefully you're understanding a little bit about what the logs are. They're talking about exponents, okay? They're looking for an exponent for the number. Okay. Let's take a look at, you know what I need to talk to you about is some characteristics here. Characteristics. So type this out. It's going to be very important. Oops. Let's make that a color you can actually see. Yellow. Characteristics of logarithmic functions. 1. For some reason my computer was muted. Sorry if someone was trying to bust in there. Characteristics of logarithmic functions. Okay. If you notice in this graph right here, and if you actually go back to the textbook and notice in 3 of these graphs right here, that the domain is restricted to the positive x. Because remember, any negatives here are undefined. And why is that? Well, 10 to the power of what would give you negative 1? You could pick any number you want for a power and you'd never actually get a negative number. You'd only get a small fraction. So you can't get a negative number by using a exponent like that. So first characteristic is the domain D is x greater than 0. X is greater than 0. So the graph only exists greater than 0. Okay, let's see. 2, the range is y can be anything. Okay, y can be anything, up, down, anything. So y is an element of all real numbers. So the domain and range, pretty important. That's supposed to be a 1 and a 2. Okay. Now, another thing, 3, notice that the intercept is, the x-intercept is x equals 1. or 1 comma 0. That's another important thing. Okay, and of course, if we have y equals a log of x space b, this a value does the same thing as exponential functions. It stretches it vertically. Okay, so I guess we could put in there for a fourth characteristic, the a value stretches the graph vertically. So all the numbers are multiplied by a, whatever a is. And even this goes down a little bit for the negative numbers, right? Times a. And point number 5 is there is no y-intercept. Okay, what does this graph look like? Well, y equals 10 to the power of x is an exponential function that you know already looks like this. Goes through y equals 1 and goes up like that. The logarithmic function is x and y are all reversed. So 0, 1 becomes 1, 0. Right? If it gets close to the x-axis here, that means that this graph would get close to the y-axis down here. And it would look something like this. So 2, 100 would be 102. So these graphs would look something like that. Now, inverse graphs, any inverse graphs are reflections about or around this line, y equals x. So it's a reflection. It's a reflection flipped around the y equals x line. When you reverse y and x, they flip. It's a mirror image around that line. And so this graph right here would be y equals log of x. And you can write base 10 or you can totally leave it out. All right, so when we're talking about logarithms, there's a special base. So we've explored base 10, obviously, base 10. We've taken a look at base 2 as well, okay? And back in the textbook here, right, they did base 10. But there's also graphs of base 2 and base 3, and you can have any base you want. Now, as it turns out, there is a special base, and the reason why it's special actually is more of a calculus thing. So it's special in calculus, very, very special in calculus. And so that means it's special to math. I'm not going to go into why it's special in calculus, but just know that when you see an exponential function and on your calculator, you'll probably see a little e, a little written or a little typed, a lowercase e. That's a special base, and it's approximately 2.71828. It's irrational. But this is a special base that's used in calculus a lot. And it has its own special logarithm name as well. So when you see this, lnx, okay, now look on your calculator. You should be able to see ln. Look at that. See ln? In my calculator, it's right underneath the log. And notice that the inverse is e to the power of x. Okay? So this is called the natural logarithm. And when you see that, don't be alarmed. Okay? And again, you don't have to know why it's special. We can talk about that afterwards if you want. But please just notice that the base e produces an exponential function that has a graph that's right in between sort of base 2 and base 3. And the logarithm is just very close to log of base 2 as well. So there's the same general shape, but that's what those buttons on your calculator are. And there'll be some questions or you have to use the natural logarithm. You just have to know what that is. Okay, and I've talked about this already, but whenever you see an a value in front of your exponential or an a value in front of your logarithmic, okay, the logarithmic function, it just stretches it vertically. So let me just flip over to Desmos here. All right, so here's this purple graph here is y equals natural logarithm of x, or log of x base e. Log of x base e. Notice that it is the inverse of y equals e to the power of x here. Okay. A regular old log base 10 looks like this. Okay. So log base 10 is a little flatter, but it's it varies the same as you know, if we had e to the or 10 to the power of x, which I don't think I have here. So let me just put that in there. Y equals 10 to the power of x. See, right there. So inverses of each other, the same way that natural logarithm of x and e to the power of x are inverses of each other. Okay. Remember the characteristics of the logs. That's the most important thing for you. Domain is greater than 0. X is greater than 0. Range is y is all real numbers. You have an intercept here at 1, 0, and there's no y-intercept. The curve also extends from quadrant 4 to quadrant 1. You're going to need to remember that. Okay? So there's a brief introduction to logs. And you can also explore what a negative a value does. We talked about that with exponentials. Same with logs. It flips it vertically if you have a negative a value. Okay. All right, so here's your assignment. You can copy that down. It's also on Google Classroom for you. And as far as the textbook goes, in case you need to see your questions on the textbook, I'll show them here on the video as well, in case you want to watch this a bit later. Oh, that's some examples.